That was very great, and I thought that I should mix them up and make something good enough. So in today's talk, there are two parts. In first half, we will talk about and learn about quantum computers, quantum mechanics, and in part second, we will go through with my project and keep your IoT module ready for that. So let us start. So before going further, I want to acknowledge you that uh, while preparing this presentation, I have used many open sources and copyrighted sources. I would like to thank the creators of them, and I apologize if I haven't cited their project enough, or I have put them on references. Uh, Let us start. So first of all, we will discuss about history of quantum mechanics and the timeline of quantum computation, how we came up with quantum computation, and how we came up with quantum mechanics. So it's all started with light. Like light is a thing that we without that we can't see. So light is a very perplexing problem from old days. Many great scientists uh, even intrigued with the problem that what is light. And so in 1672, Newton has given a theory in his book Optics that nature of light is particle, which he called corpuscles. But later, his theory was not to uh, uh, unable to describe some physical phenomena like diffraction, interference, that Huygens took over that theory, and about 200 years, the Huygens principles or Huygens optics theory was quite well. People were happy with that, and the question is still that is light particle or is light is a wave nature? But Huygens principles are working well, then people assume that it is wave. So, so what do you think? Light is made up of particles or waves? Let us find it out. So there was a scientist, Thomas Young, in 1872, have designed an experiment to create to tell that is light to answer the question that is light wave or is light made up of photons. So what was the apparatus is that he he took a light source on left side, you can see in the image, and he created a two slits whose size is much smaller than the wavelength of light used, and he projected this screen on the front screen about me of the order of meter. So like so after this experiment, he got a pattern like this. You can see here, pattern is like this. But wait, how? So you can see that the intensity of light is somewhere is very less and somewhere is very high, and you can see the black gaps in between. So why it is? So he concluded that it is wave because it is shown that light is showing interference like water waves. You can see here how water waves have crease troughs and in between. So young double experiment was quite successful, and people said, okay, light is wave. But puzzle didn't end here. So in 20th century, when quantum mechanics was started, or people thought that the classical theories are not enough to describe every phenomena, G. Broglie came with the idea of matter wave. If you have taken a higher courses in physics, then you know that the Broglie wavelength So they use similar apparatus of Thomas Young, and this time, while other than using light source, they use electron beam gun. So as expected, the electron are particles, they should not show that interference pattern, but no, they showed that same pattern, which even emphasized the need of matter wave. But Einstein was not happy with that. Einstein changed the apparatus and said that we should here before screen we should make an device. We should apply a device that can measure the presence of electrons. After using that, the pattern was like this, as you can see here. So he said, okay, electrons are particles. They can't behave like waves. But later on, Davidson and Grimmer came with other rigorous experiment. We saw that electrons show diffraction, and that concluded that we have matter waves, or we have particle wave duality. So let us come with how quantum computation come. As it is clear from name that it is made up of two names, quantum and computation. So computation done or exploited using quantum rules or quantum mechanics is called quantum computation. So how he started? It started in 1981 when Richard Feynman proposed the idea that why don't we simulate quantum mechanics on computers. As you can remember that in 1980s we didn't have quite well computers, or we do not have much computation power. So physicists still struggling with how they can do lengthy calculations like involving in quantum mechanics or other. So Richard Feynman proposes that the current state of computation is not enough to simulate quantum mechanics. So we need another stuff, or we need another paradigm for that. So in 1985, David Deshes proposes an algorithm, and why he proposes, actually people consider the Feynman's comment, okay, we need a quantum computer, but they were not impressed with that idea, that why we need a quantum computers, we are good at classical computations, why? So David Deshes uh, exploited quantum mechanics and show first advantage of if we have quantum computers, then how it can surpass classical computers. But till that time, people were not aware about that, and people were not more impressed with the idea of David Dash's algorithm that quantum algorithms or quantum computers can take over on classical. But in 1994, it was a breakthrough. Peter Shaw discovers an integer factorization algorithm on quantum computers. Which it means is that using quantum computers, you can break any cryptographic system. And when he proposed this algorithm, people were amazed that, oh, using quantum computers, we can break any crypto system. Even RSA, we can break RSA system too. So people got amazed with that and excited with this field, and people started working around that. In 1998, first working 2-qubit quantum computer demonstrated in Oxford University. And we will talk about what is qubit in a later presentation. In 2001, Shor algorithm was executed on 7-qubit NMR computer on IBM Almaden Research Center. You will learn that there is no single theory, or there is no single formulation of quantum computers. People are using very different things while doing quantum computation and making quantum computers. In 2005, first quantum byte created by scientists in Australia. And in 2017, IBM successfully tested 16-qubit quantum computers. And also, and on that time, IBM also opened a Qiskit uh, library for general public, and they also gave access to people to work and simulate their work on real quantum computers using cloud. And on that time also, Harvard announces 51 qubit quantum computers. And recently in 2019, Google also declared quantum supremacy. What it meant is that Google showed that the algorithm on classical computer, which would take about billions years, can be implemented on quantum computers and executed in some days or some minutes. That certainly shows the advantage of quantum computers over classical computations. And in 2020, we have Zhu Zhang created a Chinese scientist. Also, recently, some people and researcher team proposed a scalability idea using silicon. They made spin-tronics quantum computer using silicon, and which they showed that they can scale it like a classical computers. So we may have uh, about thousands or millions qubits in coming years. And if you see this picture right hand side, it is of IBM Q System 1, and it is an superconductor quantum computers. It is called chandelier, and the wires you are seeing hanging are the wires which are used to given quantum pulses to quantum circuit here. And the temperature of this quantum circuit is about 4 Kelvin, which is even cooler than the space. And you will happy to know that the size of this is large due to cryogenic refrigerators. So exciting and so cool. So let us start with quantum mechanics. So once Feynman quoted that, I think I can safely say that nobody understands quantum mechanics. These words have deep meanings when you will go through quantum mechanics courses, or when you start understanding it, that really no one understands what is going on real nature's problem. So if you can see this picture is quite good for quantum physics. Like in classical, we have systems which are continuous, but in quantums we have discrete system. Or you can also interpret in different sense that classical mechanics or classical physics is just an approximation of real things or quantum mechanical things. We will get to it in later on the lecture. So before going further, we should start with maths. And I would like to tell you one more thing, that quantum mechanics is full of colors. I have used some of them to make a beautiful picture, but in no sense it is complete or accurate. And I will highly encourage you people to go through with that and make your own picture, that what you find that is quite interesting. So let us start with vectors. So we know that what are vectors. Vectors are quantity which have both magnitude and direction. So we have seen this type of representation of vector, where I cap is unit vector parallel to x-axis, j cap is a unit vector parallel to y-axis, and k cap is a unit vector parallel to z-axis. But in mathematics, we use this type of representation where n-dimensional vectors can be represented using column matrices. Like you can see here, where this is a vector A that we here introduced, and this is a same notation. I also want to share with you that in quantum physics, V1 to Vn can be a complex number too. And for more advanced learner or more advanced attendee, I would like to tell you that whatever we are doing till now in our mathematics or physics, we are doing it in Euclid geometry. But in quantum mechanics, we will discuss everything in Hilbert space or Hilbert's geometry. What it means is that there is a space where there are some rules that are followed, that are not followed in Euclid. Like in Euclid, we follow Euclidean postulates, but in Hilbert there are some different rules. They are similar for our current discussion. They are mostly similar, but the difference is that in Hilbert space we can also present complex numbers that we can't represent in Euclid geometry or Euclid space. And there are many other differences that you will learn if you will go in advanced geometry courses. And I would like to tell you about eigenvalues too, that any matrix A, B is a solution of this matrix, this equation, and the set of values corresponding to that solution are the eigenvalues. And lambda 0 is a trivial solution, so it is not an eigenvalue. So lambda is not 0 here. And the corresponding matrix representation of vector are eigenvectors. They are huge importance in quantum mechanics. You will go through, when you go through in that, you will understand that why it is important. And I will also tell you that if you go through this slide, you can probably learn easily about quantum mechanics, that what is going on. So let us come with inner product. Inner product are simply dot products that we learned in our classical physics, or that we used to in our high school days. But in matrix representation, we can write inner product as this: V vector dot W vector transpose. So here is the value, and the magnitude will be like same. The magnitude is this, and this is the formula for inner product. So like we know that if the vectors are parallel, then they do not have any intersection. So they have zero dot product or zero inner product. And when they, sorry, not zero, that is maximum. And when the vectors are orthogonal, they have zero inner product. And in antiparallel, it is -1. So let us start with Dirac notation. We have different set of notation for representing quantum states. What are quantum states? Quantum states are input and output of any quantum system. Quantum states can be one or can be more than one. Here we are, qubits are the quantum states, or more specifically, qubits are 2-bit quantum states, like they represent two measurable quantities. So a cat notation is this, where this V is same as we discussed a vector, and the bra notation is this. Here V1 to Vn can be any complex number, and there is superposition, which says that alpha times 0 bit plus beta times 1 qubit. What it means is that at the same time, unlike bits, we can have two states like 0 and 1. So I would like to share with you that about history. Schrödinger proposed an thought experiment regarding this. He said that a cat is closed in a box of ammonia, or you can say poison. So the cat is in superposition of life and death, because if the bottle broke down of poison, then the cat will die, and when we open it, cat will be died. But the bottle is safe, then cat will be live, still live. That is called superposition. When overlap, I already said that the inner product shows the overlap between two vectors. So the overlap between two quantum state is this inner product. And expectation of any operator about any state is this. What it means is that, like in we have a known of mean or average value. So it is similar to average value, but it is not an average value. Okay, so expectation is similar to average value. Okay, for people who don't know about expectation can relate with that. So I discussed earlier that in ortho, when two vectors are perpendicular or orthogonal, their inner product is 0. So the inner product of two quantum state is 0 when they are orthogonal. And when they are normal, here normal means normalized. So the mode of that vector is 1. And we used to represent any quantum system using orthonormal basis. What it means that we use decomposition of any quantum state in vectors which are both orthogonal and normalized, or you can say both are perpendicular and they have mode 1. So it is block sphere where we represent our qubits. If you go in deep of mathematics, then you will understand about this more, that this is a sphere and how these coordinates are related with our Euclidean space. It is 0 bit and it is 1 qubit. And here you can see that both 0 and 1 state are orthogonal. I said that we will represent our quantum system using orthonormal basis. So their angles should be 90 degree, but you can see here it is 180 degree. That 0 qubit and the 1 qubit has angle in between about 180 degree. So why it is so? We will learn about that, why it is 180 degree. There is an historical consequences due to which we use this thing. So for advanced reader, there are other important notations that you will learn whenever you go through a quantum mechanical course, like tensor product or Kronecker product. It is similar to a product of two matrices, but in differ that order matters here. It is not commutative. And this dagger, we call this symbol a dagger, which simply means complex conjugate and transpose of any matrix. Whenever we use this operator, then we are doing what we are conjugating and transposing the matrix. And there are other products too, outer products, inner products. We will go through about them. So this is, like I told you, qubits So you will ask me, okay, you told me qubits, you told us that there exist matter waves that both are in a superposition of particle nature and wave nature, but do you have any proof that they are they are generally in two states at the same time? So STERN-GERLACH proposed both of them propose an experiment to show the existence of superposition, and here is its video. Here we're using hydrogen atom, electron, and their spin as our quantum states. Like if they are parallel to positive z axis, then it is showing 1, and if it is anti-parallel, it is showing 0. So let us watch the video for more understanding. See, these are two general magnets. So when we throw a magnet with north pole upside, so what will happen? Opposite poles attract themselves. So it is upward. But if we throw horizontally, there will be no change. It will go as it is. Likewise, we get such pattern. See, but what happens if we, instead of using these small magnets, we use hydrogen atom or electron gun? Then, like I said, that electrons have two spins, either upward or either downward. So you can see we have same different representation. They are either up, either down. But it says that we have two states, but it doesn't say that we are in superposition. Then what we will do? We will throw these electrons which are showing upward magnetic field vector in same experiment. So what should we get? We should get only upward, but we do not get upward. But if we rotate the magnets to the horizontal axis and we throw them, so we should get no reaction, or we should get horizontal, but we will not get that. You will see we will get half of them upward, half of them downward, which proposes that the electrons are in superposition of two states. And due to this experiment, the orthogonal representation, we use 180-degree instead of like perpendicular. And there is also an other thing also that you will go through when you have time about learning about Hilbert space and Euclidean space. So like in physics, whenever we propose any theory, we have certain set of rules and we have certain set of principles that we should obey while calculating things. So quantum mechanics is not a different thing. We have some principles that are observed and that are authorized by many physicists and by nature also. So first is all observable or measurable quantities in quantum physics are represented by linear operators. What does linear operators means is that operators which are linear, like when they are multiplied with scalar, they are multiplied. Like f of ax is a times x, or f of a plus b is equal to f of a plus f of b. Second postulate is possible results of measurements of any quantum states are its eigenvalues. I already told that eigenvalues have great importance in learning quantum mechanics. Whatever the results of our measurements that are represented using eigenvalues. And third, we use orthogonal vectors because they are distinguishable. The two quantum states like upspin and downspin are distinguishable because they are represented is using orthogonal vectors. And fourth one is that probability of any quantum state is a square of amplitude of its wave function. Like we will not go through about wave function. It is a difficult thing for today's discussion, but for sense of completeness, I will tell you what this amplitude means. So here, alpha and beta are the amplitudes, and amplitudes of what? If we mod of alpha and square it, then it will give us probability that we will find our system in zero quantum state with probability alpha square. And similarly, we will find our quantum system in one state when with the probability beta square. This is the meaning of our last principle. And do you remember these things, people, from Avenger Endgame, where Hulk and other Avengers use quantum mechanics to go back in time to get those stones? Actually, it is just an exploitation of a principle called principle of unitary in quantum mechanics, which says that if you go like in a quantum mechanics, operators are time involved. Like if you apply an operator on any quantum state and then apply another operator on that, then it will evolve in time. So what it says that if you applied any operator on any quantum state and then you applied an reverse operator, or you can say Hermitian operator on same quantum state, then there will be no difference on the present and the future quantum state. Or you can say in our case of Avenger Endgame or time travel, that if you applied any operator that will force you or that will throw you back in time, and you will apply another operator within reverse that you will come in future, then there will be no change in the reality or in the quantum system. So they brought the stones, and there is no change in the past and now no change in the future. This is also known as that quantum mechanics do not obey butterfly effect. So it's all about theory, what quantum mechanics is, what quantum computation is. Now we should go through with Qiskit. Qiskit is an quantum computation language, and it is an open source IBM language. There are many other languages like Google Circ and others, but some of them are open source or freely available. And Qiskit is well documented, so I use that. And first of all, we should know what is Qiskit is. You can see this flow chart. Qiskit is made up of three main type of packages: Air, Terra, Aqua. What Air package does is that Air package run your code on bare metal or run your code on real hardware. Means that this package control the microwave pulses for implementing certain gates you define. And Terra, like we need optimization too, like we have a very big circuit, so we need another library, another package too, which in background auto optimize it before running on quantum system. And Aqua, in which package we will write our code, and what we see is Aqua. We will run our circuits, or we will design our circuits on Aqua, then they, while using cloud, they will go on IBM cloud, where Terra will optimize those circuits, and in last era will implement those jobs on the real quantum hardware. And there are others too, like for more advanced application like artificial intelligence, chemistry, optimization. The abstraction levels is more abstracted than this. So, okay, you very well know about gates. We use in our classical computations like NAND gate, NOR gate, NOT gate, and any other gates. Like that, we use quantum gates to do certain operations, like this poly X gate. You can see here poly X gate. It is basically a gate which flip the bits, like in NOT gate. And I would like to point one more thing, that unlike classical gates, quantum gates are reversible. So they do not have any loss in information while implementing. For example, if you implement OR gate, so if the output is 1, you can say that what are the inputs. It can be 0, 1, 1, 0, or 1, 1. But in quantum gate, you can tell that what are exactly the inputs. It is a metric representation of this gate, X gate or poly X gate, because poly invented those gates. These are poly X, poly Y, and poly Z gates, which are higher important, and we can decompose other gates using these gates. And what is this poly gate is? It is just a rotation of any quantum state or anti-clockwise using with respect to x-axis about 180 degrees. Like you can say that if our quantum state is in 0 qubit state, if we implemented our X gate, then 180 rotated, it will go to 1 state. Likewise in poly Y, and poly Z is not an poly Z is an also known as flip change gate. Basically, there are different things. If you go in Qiskit, you will learn more about that. I will recommend you about Qiskit textbook to learn more about them. Finally, what is SUPERDENSE coding that I implemented? SUPERDENSE coding is an quantum protocol that is proposed by Charles Bennett and his team in 20th century. Like quantum channels have great property that they are secure in sense. Quantum mechanics has theorem of non-cloning, so you can't copy any quantum state. Okay, you do not copy any quantum state in quantum channels, so they are secure. Like if you transmit any message using quantum channels, then no one else can copy them. If they try to copy them, then you will get to know that, oh, our message is copied. So people propose this protocol to use quantum channels to transfer our classical information or classical bits 1 and 0. The problem is like this, goes like this. SUPERDENSE coding involves two parties, conventionally known as Alice and Bob, who are a long away from another, and their goal is to transport some classical information from Alice to Bob. Okay, so which she wishes to Bob. So how can she achieve this goal? So this is a third person, Charlie, which will entangle their qubits. What is entanglement now? Entanglement is something strange behavior in quantum mechanics that If you know part of any information, then you can recognize complete information, or you know whole information. It is something strange, and even Einstein called it spooky. You can go through it. You can. I will suggest you to go through it. EPR famous paper and Bell inequality about locality, non-locality, about the paradox. Okay, so here is Alice. Here is Alice. Here is Charlie that will entangle. This is Hadamard gate. What it does, it just change the quantum state in superposition of two states which are equally probable. Okay, so in our case there are two states, 0 and 1. So 1 by root into 1 plus 1 by root into 0, and it is Alice which will share its bits, and here Bob that will measure it. Like I told you that unlike classical mechanics or classical physics, we also, our results in quantum physics depend on how we measure things. Like if person is running with the velocity v, if you see it or not, it will be running with velocity v. But in quantum, it isn't the case. Why? If you not see or if you not measure it, it will be in superposition of running or not running. And when you measure it, you will find anyone that he was running or he was not running. That is strange, but counterintuitive, basically. That's the beauty of quantum mechanics. So let us take an 5-minute break. I will be back in 5 minutes. And till people go with my post about that, how I did it, and who people who are implementing this course with me should install Qiskit and Bolt IoT library on their local machines. And it is recommended that you should have an IBM Quantum Experience account also. I will be back in 5 minutes, not 10. In 5 minutes, I am coming. Okay.